we've been looking at these complex forms. What we're going to do today is look and see what can happen if we achieve what's called series resonance not with the fundamental frequency, but with one of the harmonics, particularly considering the harmonics might be undesirable distortion on that waveform. So that is there but shouldn't be there and can cause various range of problems on a system if it's not dealt with. Okay, so series harmonic resonance. This series resonance occurs when omega L is equal to 1 over omega C, i.e. when the capacitive and inductive reactances in the circuit at that frequency are equal to each other. Because if that's the case, we draw the impedance phasor diagram. We have the XL and the XC lines of equal length. So what we end up with, the only impedance in the circuit left is R, because the two reactive components cancel each other out. Yeah. All right. Because if these two are equal, they sum to 0. There's no J part, and all we're left with is R at resonance. Yeah. So at any other frequency, either XL or XC will take over, and we'll get some more impedance. So from the fact that all that's left is a resistance that never changes, we must have minimum impedance at resonance. It's the lowest there's ever going to be. Yeah, because the instant one of these two takes over, XL becomes bigger. We end up with a resultant in there that means more impedance. We go the other way, we end up with more impedance going. Resonance is the frequency at which those two components, XL and XC, are equal and therefore cancel each other out. Because one's positive and one's negative. Yeah? So if you can forget that part of the formula, because that cancels out, and therefore all you've got left is resistance. So whichever way you look at it, at resonance the impedance could be its minimum value, and therefore the most current's going to flow. Jasmine? Okay, so that's the situation. What we're going to do is look at we'll go through an example together, and I'll give you another example to have a go at as well. Alright? Because we'll be discussing what the possible implications are as well. So, the occurrence of resonance with unintentional harmonic frequencies has the potential for significant problems in power circuits, as the following example will demonstrate. So we've got this 2 ohm resistance inductor with an inductance of 500 millihenries and a 0.2 microfarad capacitor. We're applying this voltage here, 600 volts sine 335 pi t, and then we've got 20 volts of a third harmonic, because that figure 1005 is 3 times 335. Okay, so first of all, what we're going to do is calculate the current, or what you're going to do is calculate the current in inductor capacitor voltages at the fundamental frequency. We're assuming that that's what the circuit's been designed for. Yeah? So it's been designed to take this voltage, 600 sine 335 pi t, but there is an undesired 20 volts of third harmonic distortion. So we're going to find out what the intended current is, or what the current is at the intended frequency, and then we're going to find out currents and voltages at the third harmonic. See the difference. Okay, yeah. So how do we start on that? What have we got here? On that. Where are we going to start? If we find the total impedance at this frequency, at 335. So what's the formula for ZT for this circuit? We'll call it ZT1 as well, for ZT at the fundamental frequency. Yeah. We've got to do it from the impedances, haven't we? So it is R, we've got a resistor, plus, we'll put XL1, so it's going to be the inductive reactance at the fundamental frequency, minus XT1. J. That's the formula. Yeah. So we need to calculate XL1. That's omega 1 L, which is 335 pi times 500 times 10 to the minus 6 units or ohms. So if someone like push the buttons on their calculator and tell me what that is, please. Sorry, yeah, second, minus 3 milli. Spotted my first deliberate mistake of the term. The half term. I'm testing here. 526.2. Is that rounded to 4 significant figures, Lewis? That ain't exact. I just want to know, that's all. That's not round, that's rounded. Yeah, that's okay. And then XC2 is 1 over omega 1C, 1 over 335 pi times C is 0.2 microfarads. 10 to the minus 6 this time, Seppi, yeah? Yeah, SXC1 as well. 4, 7, 5.9, so we'll go to 1. That's the same number of significant figures then, yeah? Ohms. Alright, so therefore ZT1 is equal to the resistance, which is 2 ohms, is it? Yeah. Plus 526.2 minus 4751 J ohms. Right. Now, because we want to calculate current using Ohm's law, would probably be better to put that in polar form as well. So if we convert that to polar, to what? 526. So you can do that in one go without doing that subtraction first. What do we get? 4225 then, yeah. Ohms, angle. You're in radians, are you? No. No. We got pi in here. Okay. In fact, in essence of this problem, we aren't, although we need to include the angles and the complex quantities in the calculations, ultimately what we're interested in is the magnitude of the current, how much current's going to flow, and how much voltage is going to be across. At the end of the day, that's the magnitude we're interested in. Yeah. So now we can calculate the current. We can go therefore I1 is equal to our voltage. Fundamental frequency is 600. Angle 0 is assumed. Divided by 4225. We get 0.142 amps, angle 1.57 radians. Yeah. So at the design voltage and frequency, this circuit's going to draw 142 milliamps. Yeah. That's what's going to be drawn due to that applied voltage, which is the design voltage. Yeah. Therefore, VL1, the voltage across the inductor due to the fundamental, is I times XC. Yeah. We've got 0.142 angle 1.57 times 526.2 angle pi over 2 from inductor. Yeah. XL, that should be. And that is equal to whatever you get, and VC1 will be I times XC1, which is 0.142 angle 1.57 times 4225 angle minus pi over 2 the capacitor. $74.672 to 74.7 volts, and the angle will be pi over 2. We've got 75 volts or so across the inductor, and the capacitor oh no, hang on, yeah, got to add it together. Not that the angle is of any real significance in this answer, but we've got it, so we'll complete it. Pi over 2 plus 1.57 is what? Minus pi over 2. Ah, this one. Yeah, I've changed. 3 point what? Yeah. Sorry? 675 then. Angle's close to nothing, isn't it? Yeah. In other words, approximately nothing. Yep. So 675 volts across the capacitor. Yep. All right. So that's the situation if we only had the intended fundamental, is that we'd have a current flowing of 142 milliamps and the voltage across the capacitor be 675 volts and the voltage across the inductor 774.7 volts. Okay. So now what we're going to do is calculate the current in inductor capacitor voltages at the third harmonic frequency. Okay. So what you should find is that essentially that circuit is resonant with that frequency. So have a go. I might not be exact, but that'll be pretty close. So you'll be able to assume resonance and see what current voltages you get with that one. I'll leave that one to you for 5 to 10 minutes. Have a go. Right, so where do we start with this then? And you in? So you just follow the procedure you've done for the other frequency. Yeah. So what have you done? Yep. Good start. 1.1579 ohms. Yep. XC3 1/1005 pi. Therefore, XL3 is approximately equal to XC3. Assume resonance. You know, unless I give you an exact component value that will give resonance for one of the two components, to all intents and purposes, they're equal to each other and cancel each other out. Yeah. Therefore, ZT3 equals R equals 2 ohms. All right? Yep. Happy with that, everyone? Yeah? How do we go on from there, Ben? What have you done? Yeah. So you kept that in there, which you're going to come up with close to the same results. But I'm making. Do you see what I've done? I made the assumption that the circuit's resonant because that's what we're interested in. Yeah. Component tolerances would allow that to fall in there somewhere, possibly. Remember, we're considering what might happen if accidentally resonance happened in this circuit. All right, so down to component tolerances, that may well happen. Okay, perhaps I didn't explain. But I did say, make the assumption of resonance. Okay, therefore, I3 is equal to V3 over ZT3. What's the voltage of the third harmonic? 20 volts divided by 2 ohms equals 10 amps. Yeah? Alright. So, we'll look at the implications of that in a minute, but we're going up from 142 milliamps flowing due to the intended voltage. We've got 10 amps of third harmonic current flowing in the circuit. Okay, so we'll think about the implications of that in a minute. Then VC3 is equal to because we're resonant, VC3 and VL3 are essentially equal to each other and are equal to I times, we'll take XL for one. We've already said they're equal to each other, so we've got 10 times XL was 1579. Equals 15.79 kilovolts. So we've got a circuit being supplied with an intended 600 volts. We've got two components with 15k volts. An extreme example, yes, perhaps, but thinking about the implications. Okay, we've got calculations that demonstrate a 10 over 0.142, i.e. approximately 70 times increase in current flow to the third harmonic voltage being present. There's also a 212 time increase in the inductor voltage and a 23 times increase in the capacitor voltage. What do we think the implications are for the components of the circuit? Boom. Yeah. Let's think of the current first. Hopefully, circuit is correctly protected for overcurrent. Cause boost to blow for circuit breaker trip, CB trip. That was what you would hope would happen. Yeah. If not, cable and inductor overload, overheat and burn out. Yep. So what you'd hope is that that circuit is correctly fused, correct circuit breaker has been chosen, and enough current flows to trip that or blow the fuse. Yep. If that doesn't happen, then we're looking at an inductor intended to carry, let's say, half an amp, carrying 10 amps. That's highly likely that's going to overheat and burn out. Okay, just depends on what the component is really. Yeah. Voltage. Capacitor. Capacitor, as well as its capacitance, it'll have a working voltage greater than 600 volts, but not 15 kV. Yeah. Therefore, dielectric breakdown. Capacitor destroyed. Usually open circuit, innit, Chris? With a big bang. Lots of paper everywhere, if they're paper capacitors. Okay? Yeah. Yeah. Overload, stroke, overheat. Yeah. All right. Inductor. The insulation of the inductor could well not withstand 15 kilovolts for any length of time. So although the insulation is an insulator, there are limits as to how much pressure you can apply without causing breakdown. So we may get insulation problems with the and other circuit components. All right. Yeah. Not a good idea, really. Sorry? Well, to let resonance happen. Just to give you an idea of where that might happen, and that I've read a couple of articles that say that's kind of difficult problem to find, because you might get spurious tripping of circuit breakers and not understand why it's happening, because everything else appears to be the same. But when you what happens in power systems, when you have lots of inductive load, which big factories might have lots of motors, you end up with a power situation. You've got this power triangle where you've got P on the horizontal axis. This is similar to what we've done with complex numbers and currents and such things out of phase. We've got inductive power, which is called Q, and then we've got the apparent power, S. And this angle in here, the cosine of that angle, is called the power factor. And the more inductive load you've got, the longer this line gets up here, the longer the S line gets, and the current increases for no more power. So what we have is power factor correction. And what they do is they add capacitance into the circuit, so we get an opposite action down here from the capacitor that draws this S line closer to the P line, therefore reducing the current. I don't want to go too deep into that subject, but big companies will have automatic power factor correction capacitors that switch in and out as the load changes. If the steps in them are not tuned correctly, you could end up with a resonance situation. Because what they'll do is they'll have a banks of capacitors that switch in and out, so they're not constantly variable, infinitely variable over a range. They'll be ranged in steps. And if those steps aren't carefully chosen to avoid resonance, then you could get this problem accidentally. Okay? So just to give you a kind of a very basic background as to one reason why this might happen. Power factor correction. If you carry on your studies with us next year, we'll look at power factor correction more fully in the level 6 module. All right. So in your notes, you've got a second example similar to that one. Have a go at. I'll try to build in a bit of a rating to the circuit, and for you to show that if we've got an inductor whose maximum current rating is 2 amps and that has a resistance of 14 ohms, I think those values are pretty close to the big inductor that you used in science, if you remember, the one with the adjustable core to do your science. Not you, Jasmine, because you didn't do that course, but these guys did. All right. Inductance value is 670 millihenries, and are connected in series with a 1.68 microfarad capacitor with a working voltage of 125 volts. So show that it would be okay to apply 60 volts at 50 hertz, omega's 100 pi, but not to apply 60 volts at the third harmonic, which is 150 hertz. Okay, so through calculation, demonstrate that you'd be all right to apply 50 hertz, but not okay to apply 150 hertz because of resonance. Yeah. So you're going to compare the results you get with the rated current of the inductor and the rated working voltage of the capacitor. All right. and I'll put the working of the result for this on second part of the video for those watching.